On November 14th, 2023, Voyager 1 abruptly went quiet, transmitting back nothing but a meaningless stream of binary data. It appeared the spacecraft, which had journeyed beyond the solar system, was gone for good. The cause turned out to be a memory failure in its onboard flight data system, FDS, threatening a permanent loss of communication. Yet the team of scientists refused to give up. They made the bold call to reallocate code to other areas of the probe's memory. This process started on April 18, 2024, and carried significant risk. The signal took 22.5 hours to reach Voyager, and the same amount of time for a reply to come back. Every attempt was a leap into uncertainty. Just 2 days later, after months of intense effort and anticipation, something remarkable happened. Voyager 1 re-established contact. What extraordinary discoveries did the Voyagers make at the edge of the solar system? Why did things turn out so different from what scientists had envisioned? And what was contained in the mysterious signal Voyager 1 sent after months of eerie silence? In the late 1970s, a rare event took place in the solar system, a planetary alignment that occurs only once every 175 years. At that moment, the gas giants lined up on one side of the solar system, creating a unique chance to study them all in a single mission. NASA jumped at the opportunity. Voyager 1 launched after its twin, but overtook Voyager 2 thanks to a shorter trajectory, reaching speeds of 38,000 megapolar compared to Voyager 2's 34,360 nautical. Just 13 days after launch, it captured a historic photograph of Earth and the Moon from 7.2 million miles away, which became a symbol marking the start of their grand journey. In 1979, both probes arrived at Jupiter, revealing rings no one knew existed, discovering 3 new moons, and capturing detailed images of its largest satellites. They confirmed that Ganymede is the largest moon in the solar system, not Titan, as previously believed. They also found that Europa's surface is covered in smooth ice riddled with cracks, data that gave rise to the hypothesis of a subsurface ocean, something we've covered in another video. Additionally, the scientists got their first close-up view of Jupiter's Great Red Spot, a centuries-old storm larger than Earth itself. Jupiter was only the beginning of their grand journey. Using its gravity for a speed boost, both probes reached Saturn in 1980 and 1981. This marked a turning point for the Voyager mission. It was originally planned to last just 4 years, covering Jupiter and Saturn, but NASA designed the mission's trajectories so it could potentially extend to other planets. A key decision was made to fly close to Titan, the only moon in the solar system with a dense atmosphere. Ultimately, Voyager 1 was directed toward Titan, sacrificing its ability to continue onward, while Voyager 2 was sent toward Uranus and Neptune. The probe sent back detailed images of Saturn and its rings, revealing they're made up of hundreds of narrow, intricately structured rings. 4 new moons were also discovered. Mima's was of particular interest, notable for being covered in craters, including the massive Herschel crater, giving the moon a striking resemblance to the Death Star from Star Wars. Titan, however, held an unwelcome surprise. Its atmosphere was opaque to visible light, blocking any view of its surface. Still, analysis showed Titan's temperature was close to the triple point, a unique condition where methane behaves similarly to how water does on Earth. After Saturn, the paths of the 2 probes split forever. Saturn's gravity gave Voyager 1 a major boost, altering its trajectory and making it the fastest spacecraft in history. Voyager 2, meanwhile, continued its planetary tour, heading for Uranus next. It reached Uranus in January 1986, coming within 50,600 miles of the surface. Scientists were surprised to find Uranus was vastly different from Jupiter and Saturn. While the gas giants are made up of 90% hydrogen and helium, Uranus contains these elements only in its atmosphere. Beneath that lies an ocean of water, ammonia, methane, and hydrogen sulfide, with a core of rock and ice at the center. Later, planets of this type came to be called ice giants. Uranus also turned out to be the coldest planet in the solar system, even colder than Neptune. After gathering data at Uranus, Voyager 2 moved on to its final target, Neptune. It arrived in August 1989 and remains the only spacecraft ever to have visited the 8th and most distant planet in the solar system. On August 25, 1989, Voyager 2 captured the first detailed images of Neptune, completing its grand tour. The planet appeared vividly blue, though later data revealed its true color is closer to teal. While Voyager 2 explored Uranus and Neptune, Voyager 1 could only envy its twin. After its Saturn mission, engineers shut down a large portion of its instruments, leaving only the technology needed to study its surroundings. Still, Voyager 1 got one more chance to make history. On February 14, 1990, from 3.72 billion miles away, it captured Earth as a tiny pale blue dot, just 0.12 pixels in size. This iconic photo, known as the pale blue dot, became the final image ever taken by Voyager 1 before the cameras on both probes were shut down permanently. Our cosmic travelers then entered a long, quiet stretch lasting a decade and a half. interrupted by an extraordinary event on August 25, 2012. Voyager 1's instruments recorded a sharp drop in charged particles coming from the Sun, along with a rise in galactic cosmic rays. This signaled that the spacecraft had finally entered interstellar space, leaving the region where the Sun's influence ends and interstellar radiation takes over. The slower-moving Voyager 2 crossed the same boundary in November 2018. The unique bubble surrounding our solar system, called the heliosphere, extends roughly 11 billion miles from the Sun. It's formed by the solar wind, a stream of particles from the Sun, and ends at the heliopause, the boundary between the heliosphere and interstellar space. The Voyagers are the only spacecraft to have crossed this boundary and left the solar system. What they found out there sparked widespread interest and debate among scientists. It was previously thought the solar wind gradually fades as it moves farther from the Sun. But data from the probes showed the solar wind doesn't fade gradually. Instead, it hits a sharp boundary. Beyond that boundary, its influence stops and interstellar space begins. This means the solar wind doesn't simply dissipate, but instead changes direction, forming a physical boundary between the two environments. The solar wind flows around the heliopause from inside, while interstellar plasma flows around it from outside. Scientists were also able to work out the shape of the heliosphere. On one side, it resembles a sphere, while on the other, it stretches into a long tail. Curiously, the shape isn't fixed. The boundary of the solar system is constantly shifting. The surface of the heliosphere is distorted by massive waves appearing at unexpected uneven angles. These waves can reach 10 astronomical units, 10 times the distance between Earth and the Sun, or about 930 million miles. Additionally, by studying Voyager data, scientists found that the heliopause underwent rapid changes over a short span of time, which may explain why there was such a large gap, 6 whole years, between when the two probes crossed the heliosphere boundary. However, these shifts in the heliopause contradict existing scientific models and remain unexplained. Likewise, the temperature and density of the solar wind near the heliopause defy explanation. Astrophysicists expected that as interstellar radiation slowed solar particles, temperature and density would spike sharply. While that did happen, the measured values were 10 times lower than theoretical predictions. Where that missing energy went remains unclear. Data from Voyager 1 and Voyager 2 also revealed that interstellar space consists of denser, colder plasma, while plasma near the solar system's boundary is hotter and less dense. Notably, these two types of plasma interact. Particles from the solar wind mix with interstellar particles, creating a kind of boundary layer between the heliopause and interstellar space. But the interaction between the Sun and interstellar space doesn't stop there. Shock waves from the Sun can pass through the heliopause into interstellar space, creating disturbances similar to the shock waves generated by supernovae as they spread through interstellar space. Thanks to the Voyagers, scientists also learned that the interstellar magnetic field is 2 to 3 times stronger than previously believed, meaning interstellar particles exert 10 times more pressure on the heliosphere than expected. The data gathered from this interaction gives us a fuller picture of what happens between the Sun and interstellar space, insights that can be applied to other stars being studied by astronomers, since other stellar systems likely share similar properties and processes with our own solar system. Throughout their journey through interstellar space, the Voyagers have kept sending signals back to Earth, transmitting data about their instruments' status and their locations. However, in 2022, Voyager 1, while 14.6 billion miles from Earth, unexpectedly began transmitting a strange signal, chaotic data about its position, consisting of sequences of zeros or the number 377. This puzzling signal left scientists uncertain whether it contained critical information or signaled a malfunction. It turned out to be the latter. The issue was tied to the spacecraft's attitude control and maneuvering system. Although it was still possible to control the spacecraft manually, Voyager 1 had lost precise awareness of its position, likely due to cosmic radiation affecting its navigation system. NASA engineers resolved the issue by routing telemetry through a different onboard computer. Another alarming event occurred when Voyager 1 went silent for an extended stretch starting November 14, 2023, lasting 5 months. This was caused by corrupted code on one of its chips. To fix it, the team decided to move the code to other sections of the onboard computer's memory. The data transfer process began on April 18, 2024, and required considerable patience. After sending a signal, the team had to wait 22.5 hours for it to reach the spacecraft, then another 22.5 hours for a response. By April 20th, the team confirmed the operation had succeeded, and after 5 months, scientists were able to restore communication with Voyager 1 and confirm it was still functioning. These malfunctions are a reminder that our cosmic travelers' lives are drawing to a close. NASA hopes the Voyager's instruments will keep working until 2025, after which a gradual shutdown will begin. In a few years, the spacecraft will lose the power needed to communicate with Earth, likely around the mission's 50th anniversary. marking the final chapter of this project. Even after contact is lost, these cosmic travelers' journeys will continue. They may encounter many fascinating phenomena, though they'll no longer be able to report back on them. Voyager 1 is moving away at roughly 3.5 astronomical units per year. 1 astronomical unit being the average Earth-Sun distance, about 93 million miles or 150 million kilometers. Voyager 1 is currently headed toward the constellation Camelopardalis. In the year 4272, some 38,200 years from now, it will pass within 1.7 light years of an obscure star in the constellation Ursa Minor called AC plus 793888. Its twin, Voyager 2, is leaving the solar system at about 3.1 astronomical units per year. Around 40,000 years from now, it will pass within roughly 1.7 light years of a star called Ross 248, a small star in the constellation Andromeda. Currently, Voyager 1 is about 15.5 billion miles from Earth, while Voyager 2 is 12.4 billion miles away. Although they passed beyond the Sun's heliopause long ago, it's not entirely accurate to say the Voyagers have fully left the solar system. Scientists consider the solar system to include everything within the Sun's gravitational reach, and it's thought the outer limit of that influence is the Oort cloud, a hypothetical spherical region surrounding the solar system that serves as the source of comets that periodically pass through our planetary system. The Oort cloud consists of 2 distinct regions, a spherical outer cloud and a disc-shaped inner region. The outer edge of the Oort cloud is estimated to lie somewhere between 50,000 and 100,000 astronomical units from the Sun, roughly the distance light travels in a year. Voyager 1 will take about 300 years to reach the inner edge of the Oort cloud, and possibly another 30,000 years to pass through it entirely, marking its true departure from the solar system. Should the spacecraft ever encounter extraterrestrial life on their distant journeys, they carry messages prepared by a team of scientists, including a phonographic record on a gold-plated copper disc containing roughly 34 recordings of music. The disc also includes greetings in various languages, messages from the U.S. President and the UN Secretary General, sounds of Earth, human voices, whale songs, brainwave recordings, and more. Plenty to keep any aliens occupied. But if the Voyagers are never found, they'll simply keep drifting through the dark, cold void of interstellar space, standing as a symbol of humanity's pursuit of knowledge and a reminder to the universe of the ambitions and hopes of the inhabitants of one small pale blue dot. In 1977, Voyager 1 and Voyager 2 launched from Cape Canaveral, less than a month apart. Voyager 2 actually launched first, but because it followed a different flight path, it reached the edge of the solar system 6 years after its counterpart. Both spacecraft uncovered a very strange anomaly. As you move farther from the Sun, the density of space actually increases. Interstellar space is usually thought of as a vacuum, but that's not entirely accurate. Matter density is extremely low, but it's still present. Within the solar system, the solar wind has an average proton and electron density of 3 to 10 particles per cubic centimeter, dropping the farther you get from the Sun. The lowest density in the solar system occurs at its very edge, a boundary called the heliopause, where the speed of the solar wind, the stream of charged particles emitted by the Sun, also called solar plasma, drops to 0. The region between the Sun and the heliopause is the heliosphere, a kind of bubble containing all the planets of the solar system. At this boundary, the density of protons and electrons is 0.002 particles per cubic centimeter. Calculations suggest that beyond the heliopause, in interstellar space, the density should be 0.0037 particles per cubic centimeter. Voyager 2's instruments showed that at a distance of 119.7 astronomical units, or 17.9 billion kilometers from the Sun, the density outside the solar system was 0.039 particles per cubic centimeter, nearly matching the calculations. But then things got strange. At 24.2 astronomical units farther out, or 18.5 billion kilometers, the density was 0.12 particles per cubic centimeter. Why is the density increasing? We'll get into that shortly, but first, let's look at another bubble, one far larger than the heliosphere, so you can appreciate how the cosmos has, in a way, packed us into 2 bubbles at once and understand how the 2 relate. When you look at images of deep space, it seems filled with clouds of interstellar dust and glowing gas. But back in the 1970s and 80s, astronomers began noticing that the galactic region around the Sun looks different from that picture. The solar system appeared to sit in an almost total void. This year, scientists at the Harvard-Smithsonian Center for Astrophysics, CFA, confirmed that yes, we really are inside a kind of void. Using highly complex computer simulations, they built a 3-dimensional reconstruction of space and time. The study found that the Sun and Earth sit almost at the center of a giant bubble, roughly 1,000 light-years across, which they named the local bubble. Calculations suggest it began forming about 14 million years ago, requiring roughly 15 supernovae to explode over several million years. This series of explosions pushed interstellar gas outward under the pressure of light, forming a bubble-like structure with a dense surface at its edge. And the bubble is still growing today. When it first formed, it was expanding at about 60 miles per second. According to data from the European Space Agency's Gaia Space Observatory, it's now expanding at 4 miles per second. 7 star-forming regions, dense molecular clouds where stars are born, have been detected on its surface. Star formation happens all across the surface of the local bubble, and there are many similar bubbles scattered throughout the galaxy, meaning other stars, possibly with planets, could exist within their own local bubbles too. Interestingly, the Sun wasn't originally at the center of this structure. When the initial explosions occurred, the Sun was about 1,000 light-years away from the site. But as astrophysicist Catherine Zucker of the University of Vienna explained, roughly 5 million years ago, as it orbited the galactic center, the Sun ended up almost exactly at the bubble's center. This lines up with estimates based on radioactive isotope deposits from a supernova found in Earth's crust. Researchers from other studies suggest there are probably more star-forming bubbles scattered across the Milky Way. Lead researcher and CFA astronomer Alyssa Goodman, who developed the visualization software GLUE, noted in her statement that statistically, the Sun wouldn't likely be near the center of such a huge bubble unless bubbles like this were common throughout the galaxy. The local bubble is exactly the bubble we're in right now, she said. We think the Sun has probably passed through a number of these superbubbles over its history. The scientists compared the cosmos to Swiss cheese. Supernova explosions punch out the holes, and new stars form along the edges of those holes as older stars die. The research team plans to map out more cosmic bubbles to build a full 3D picture of their shape, location, and size. By charting where these bubbles lie across space, astronomers can piece together how they act as nurseries for new stars, how they interact with one another, and how galaxies like the Milky Way have evolved over time. With the discovery of the local bubble, here's how the structure of the solar system now looks. At its center is the Sun, orbited by 8 planets, the outermost being Neptune, roughly 4.45 billion kilometers, or 30 astronomical units away, 30 times farther from the Sun than Earth is. Beyond Neptune lies the Kuiper Belt, a collection of small celestial bodies, the most famous being Pluto, long considered a planet. The Kuiper Belt extends out to roughly 55 astronomical units. Farther still, between 125 and 135 astronomical units, lies the heliopause, which we've already described. Let's explain why density starts rising at this boundary. It happens because solar plasma collides head-on with interstellar plasma. Picture 2 streams crashing into each other at cosmic speeds. Naturally, density increases at the point of collision, much like a traffic jam, a chaotic pileup of particles. Beyond that jam, at a distance of 0.75 to 1 light-years, lies the Oort cloud, a spherical shell of up to 1 trillion icy objects that serves as the source of long-period comets. Here, the interstellar wind already dominates, but the Sun still holds these bodies within its gravitational grip with its last bit of strength. Naturally, some viewers might ask, we're inside a bubble that's enormous by earthly standards, even within a double bubble, the local bubble and the heliosphere. So what? How does this actually affect our lives? Regarding the smaller bubble, the heliosphere, we can say clearly that thanks to that traffic jam forming at its border, Earth is well shielded from high-energy cosmic particles streaming in from the galactic center. As for the local bubble, scientists have long known that our galaxy, the Milky Way, has a spiral disk shape, with several spiral arms extending from its center. Right now, our Sun sits roughly halfway between the Sagittarius arm and the Perseus arm, and it orbits the galactic center once every 200 million years, what's called a galactic year. Only 0.08 of that year has passed since humans first appeared. Along its path, the Sun and its planets have crossed not just bubbles, but also dense accumulations of interstellar gas, where matter density spikes hundreds of times over. Astrophysicist Mikhail Filipovich, using the latest model of the Milky Way, examined what happened on Earth whenever the Sun crossed these galactic arms, where interstellar density is much higher. He found a correlation between the timing of the Sun's crossings of the spiral arms and 5 known mass extinction events: 415, 322, 300, 145, and 33 million years ago. So it's reasonable to think that right now, the Sun sits in a quiet, favorable harbor for life, and that humanity is fortunate to have emerged on Earth while the Sun was passing through the local bubble. Whether that's coincidence, or whether humanity's appearance and the Sun's presence in this safe haven are somehow connected, science doesn't yet know, at least not for certain. But we can say for sure that the vivid, star-filled sky we see is only visible because we're essentially sitting in a void, the local bubble. If the space around us were denser, many stars would be hidden from view, and who knows how much we'd understand about space and the structure of the universe if we were truly in the dark. In a sense, the local bubble is a gift to humanity as it enters the space age and begins reaching for the stars. For an interstellar craft traveling at sublight speeds, the biggest danger is dust particles, which could grind a ship down during collisions. Even hypothetical spacecraft designs call for a frontal shield. But it turns out the cosmos has already cleared much of that dust from the space around the sun, as if clearing the way and saying, the path to Alpha Centauri and beyond is open. Stay tuned for more updates on humanity's greatest achievements. Thanks for watching. It might seem like space is an empty, abandoned place, showing no sign of any other civilization like ours. But does that mean the universe is completely silent, and that nobody besides us has tried to explore it? Recent scientific discoveries suggest otherwise. The farthest space probe, Voyager 1, has been traveling for nearly 44 years and still sends data back to Earth. One day, scientists picked up a strangely eerie cosmic hum. Even though the probe had sent similar recordings before, this newly detected signal was notably different. For the first time in human history, we had a chance to explore what lies beyond our solar system. The signal was detected more than 14 billion miles from Earth, a steady 3 kilohertz sound that persisted for almost 3 years straight. This is the most stable, longest-lasting hum ever picked up by Voyager 1, and scientists were only able to detect it once the spacecraft had traveled far enough. So where does this eerie sound come from? Most scientists believe the hum results from plasma waves moving through the depths of space, plasma being a fundamental material that makes up nearly all cosmic objects. What's remarkable is that this sound stayed nearly constant even after the probe traveled another billion miles, a level of consistency that has led some scientists to suspect there's an unknown source of energy behind it. But how can there be sound in space at all? True, sound fades almost instantly in the vacuum of space, since there aren't enough particles to carry it. Even massive events like black hole collisions or supernova explosions produce no audible sound there. Here's a simple demonstration. Place a small bell inside a plastic bottle and screw on the cap. Shake the bottle and listen to the bell. Now remove the lid, drop in 2 lit matches, quickly reseal it, and let them burn out. Once the air inside cools, shake it again, you'll notice the sound is much quieter, or barely there at all. Still, certain electromagnetic waves, including radio waves, travel through a vacuum without any trouble. Although human ears can't detect such signals directly, scientists have found ways to convert them into sound, allowing us to hear the message Voyager 1 sent us. So how did Voyager 1 manage to pick up such faint signals and transmit this data back to Earth? The spacecraft is equipped with 2 highly sensitive antennas designed to detect plasma variations in space and record them. Even traveling at the speed of light, these radio signals take more than 20 hours to cover the distance. Unfortunately, we won't be receiving signals from Voyager 1 for much longer. It's currently running low on power, and its critical instruments may only keep functioning for another 3 or 4 years. Still, Voyager has already exceeded every expectation, and it may yet surprise us with more groundbreaking discoveries in the years ahead. Even though this latest finding is a big deal, NASA has stumbled upon other strange sounds before. In 2007, researchers unexpectedly discovered something bizarre buried in years-old data: fast radio bursts, or FRBs. These bursts are incredibly brief, each lasting only about a millisecond. Since then, researchers have continued searching for more FRBs and found plenty. Here's what these radio bursts sound like. It seems the more we learn about the universe, the more questions arise. Could these be an attempt by an intelligent alien civilization to reach out to us? Or perhaps they weren't meant for our eyes and ears at all. NASA has also occasionally picked up eerie sounds much closer to home within our own planetary system. Take Jupiter's moon, Ganymede, for example. Here's the unsettling sound it produces. In reality, these sounds come from chorus waves, coherent electromagnetic waves that frequently trigger auroras, or polar lights. Earth isn't the only place where this striking phenomenon occurs. It also happens on Saturn, Jupiter, and Ganymede. So what you just heard is essentially a converted recording of polar lights on Ganymede. And what about Mars? We've studied it extensively, and NASA's Perseverance rover recently captured something intriguing: the first actual recording of the rover driving across the Martian surface. Interesting enough on its own, but alongside the sound of its metal wheels rolling over rocky terrain, Perseverance also picked up an unidentified, high-pitched scratching noise. Here's the actual recording sent back by Perseverance. Nobody knows what's causing this scratching sound, and while NASA scientists work to figure it out, the mystery remains unsolved, leaving plenty of room for speculation. This would mark humanity's first major step into interstellar territory. The mission's core goal is to capture an image of our entire solar system from a huge distance and continue exploring interstellar space, bringing us closer to understanding our place in the universe and unraveling the mysteries of deep space. In the history of spaceflight, only 5 spacecraft launched by humanity have had enough momentum to leave the solar system entirely. The Voyagers are 2 of them, and they've ended up discovering far more than anyone anticipated, lasting much longer than NASA ever predicted. NASA later renamed them because these 2 spacecraft had advanced well beyond the capabilities of the earlier Mariner family. In other words, they were far more sophisticated. Speaking of which, it's worth taking a closer look at the technology and hardware packed into these vintage probes. Launched an astonishing 44 years ago, Voyager 2 on August 20th, 1967, and Voyager 1 2 weeks later on September 5th, 1977, these missions came at a time when major advances were being made in gravity-assisted orbital trajectories, essentially allowing a spacecraft to use a nearby planet's gravity to gain a substantial boost in speed, as long as it follows a precisely mapped-out path. Let's start with the computers, which are identical on both spacecraft. Each Voyager computer system is dual redundant, meaning there are 2 of everything in case one system fails. Each probe's computers have just 69.63 kilobytes of total memory, barely enough to store an average-sized JPEG photo. Scientific data on each probe is recorded using old-school digital 8-track tape machines, though nothing like the 8-track stereo you might picture in a classic muscle car. No physical examples of this hardware survive today, not even in a museum, but a photo does exist. This is the tape recorder subcontracted to Lockheed and built by Odetics for both Voyager spacecraft. It could record data at 2 speeds, 115.2 kilobits per second and 7.2 kilobits per second, while playback topped out at a slower 57.6 kilobits per second, with 33.6, 21.6, and 7.2 kilobits per second also available as options. Exactly what the magnetic tape was made of, and how it was kept from degrading in the harsh conditions of space, remains unclear, but whatever the secret, it worked, since the tape recorders on both spacecraft performed flawlessly from launch all the way through the Grand Tour and the extended mission that eventually sent both probes beyond the solar system. The Voyager computers can execute about 81,000 instructions per second. Your smartphone is likely around 7 million times faster than that. They transmit data back to Earth at just 160 bits per second. At that speed, downloading a 5 gigabyte movie from Netflix would take about 8.5 years. But perhaps the most fascinating item aboard each spacecraft is something no other probe carries: a golden phonograph record. Instead, let's look at some of the standout discoveries and images captured during their missions. Both spacecraft have traveled along different trajectories and at different speeds. Voyager 1 moves faster, at about 61,500 kilometres, compared to Voyager 2's 56,827 kilometres. Voyager 1 captured striking images of Venus, Jupiter, Saturn, Uranus, and Neptune, along with an incredible shot of Jupiter's moon Io, where a volcano was seen actively erupting, the first time an active volcano had ever been observed elsewhere in the solar system. But Voyager 1's most famous image is undoubtedly the pale blue dot, its now iconic photo of Earth, taken on February 14, 1990, from 6 billion kilometers away, which inspired the title of Carl Sagan's book, Pale Blue Dot, A Vision of the Human Future in Space. Voyager 2, meanwhile, began transmitting images of Jupiter on April 24, 1979, which were compiled into a time-lapse movie showing the gas giant's swirling atmosphere, including its famous Great Red Spot, a storm 3 times the diameter of Earth. Voyager 2 achieved this partly because it made closer passes to Jupiter and its moons. On August 25, 1989, Voyager 2 flew past Triton, one of Neptune's moons. The data it collected was used to construct a video of that flyby, giving us views of Jupiter unlike anything seen before. Together, Voyager 1 and 2 explored every giant planet in our solar system, 48 moons, a unique ring system, and the magnetic fields of each outer planet. But that wasn't the end of what they discover, as you're about to see. In fact, they were about to encounter something far more mysterious and unexpected, something they weren't even built for. Voyager 1 crossed into interstellar space on August 25, 2012, becoming the first human-made object to do so. As it left the heliosphere, the giant bubble of charged particles surrounding the Sun, the probe recorded a 1,000-fold drop in heliosphere particles, alongside a 9% rise in galactic cosmic rays, originating from outside the solar system. Since entering interstellar space, Voyager 1 has sent back valuable information about conditions in this uncharted region. Among its findings, cosmic radiation out there is remarkably intense, and its data illustrates how particles from the Sun interact with particles from other stars, and how the bubble of charged particles surrounding our solar system shields everything inside it from those dangerous cosmic rays. On November 5, 2018, Voyager 2 became the second spacecraft ever to reach interstellar space, when it registered a sudden drop in solar wind particles from the Sun, alongside a rise in galactic cosmic rays and a strengthening interstellar magnetic field. Voyager 1 has continued to impress engineers as well. In December 2017, it successfully fired up its backup thrusters to reorient itself for communication with Earth, thrusters that hadn't been used since November 1980 during its Saturn flyby. That's quite a testament to their reliability. The Voyager probes are constantly transmitting a signal. Each carries a 22.4-watt radio transmitter, roughly equivalent to a small refrigerator light bulb. Remarkably, by the time that signal reaches Earth, its power has dropped to about a tenth of a billionth of a watt. It's so faint that NASA relies on its deep space network, made up of giant radio antenna arrays at 3 facilities spread across the globe: the Madrid Deep Space Communications Complex, the Canberra Deep Space Communication Complex in Australia, and the massive 70-meter antenna at the Goldstone Deep Space Communications Complex in Barstow, California. The sensitivity of these tracking antennas is remarkable. They capture Voyager's signal even though the power reaching the antenna is only 10 to the negative 16th watts, a level roughly 20 billion times weaker than the power used by a modern digital watch. And we're still not done hearing from the Voyagers. On October 29, 2020, mission operators sent a series of commands to Voyager 2 following a 7-month silence, during which the spacecraft had been operating solo while the 70-meter antenna at Goldstone underwent repairs and upgrades. Remarkably, even after all these years, and despite being deep in interstellar space, Voyager 2 confirmed receipt of the commands and executed them without a hitch. As of January 2022, Voyager 1 sits 23.3 billion kilometers from Earth, and Voyager 2 is 19.3 billion kilometers away. Most instruments on both probes have been powered down to conserve energy. Voyager 1 is heading toward the constellation Camelopardalis, and in the year 4272 AD, it will pass within 1.7 light-years of an obscure star in Ursa Minor called AC Plum 793888. In about 40,000 years, Voyager 2 will come within roughly 1.7 light-years of a star called Ross 248, located in the constellation Andromeda. Sadly, well before either of those milestones, we'll lose contact with both spacecraft for good, and they'll drift silently into the interstellar void. It's intriguing to imagine that someday, far in the future, some distant civilization might stumble upon a Voyager probe and figure out how to power it back on, giving that primitive hardware one last moment of life. Stay tuned to see whether the Voyagers uncover anything new, to keep up with all the exciting developments happening across our universe. Thanks for watching.